Welcome to Old School Chemistry. Today we're going to do the ALEKS topic, drawing the reaction energy diagram of a catalyzed reaction. So let's talk about catalysts, how they relate to rate of reaction. Here it is. A catalyst decreases the activation energy, which in turn increases the rate of the reaction. We're not 100% sure how this works. We think it changes the mechanism of how reactants break and how products form. Now, in an activation energy diagram, here's how that applies. Here's how we graph that. So here's an exothermic reaction. It takes less energy to break the reactants than the amount of energy that's released when those products formed. So you have a net release of energy, exothermic. In the purple, I drew our activation energy diagram. The minimum energy required to break those reactants for the reaction to happen is going to be your E of A. Now you add a catalyst to that. It decreases the E of A. That's in the blue. See how that's a smaller activation energy in comparison? We call that E of A catalyzed because it takes less energy for the reactants to change to products. The reaction is going to go faster. Now in an endothermic reaction, it takes more energy for reactants to break than the energy that's released when products are formed. So it takes a net absorption of energy for that reaction to happen. Here you can see the minimum energy required for the reaction to begin our activation energy. Wow, that's big, okay? And, oh, sorry, I did my arrow wrong here. On our E of A catalyzed, look, it's smaller. There's your E of A, energy required for the reactants to change to products. And here, because the activation energy is lower, it takes less energy with the catalyst present, so it's going to go faster. Now, drawing this, there's a drawing tool that you need to be comfortable with. First thing that I notice on this is the word endothermic. In fact, let me highlight that word. Let me circle that word. With ALEKS, it's usually every other one. You'll do one as endothermic, then you do the next one that's exothermic. Make sure that you look if it's endo or exo. So endothermic, I know that I'm going to start low. You click on the reactant with his hand and drag it. So I'm going to start there. And then we're going to end higher. So here's my big activation energy. And then here for my product, I know that I'm going to end higher than my reactant. Takes more energy here to break reactants than the energy released when products are formed. So here we've got our activation energy. Now you can start anywhere, you can end anywhere as long as you have the correct shape. You do want to be thinking though that you have to draw similar with the catalyzed, and the only thing that you change is the height of the activation energy. So two things, you have to keep the product and reactant the same, and number two, you change the peak, the activation energy, the height of the activation energy. So here I'm going to start the same. Notice it has this guideline. If I click that again, you can see the guideline. Let me come down, you can see that guideline. And then up here, I'm going to make my product match. So for my activation energy, there it's matching, I simply come down. And I tell my students, you only have to come down one. As long as it's lower, you're showing it's been catalyzed. So you have beginning, same spot on reactants and products. The one thing that's going to change is the height of that activation energy, and the catalyzed will always be lower. Let's go ahead and check this, and I want to do an exothermic with you. So notice on this one, there it is, exothermic, you can see, exothermic. I'm going to begin higher. We're going to have our activation energy, and then we're going to end low. Now I match. I have to match the reactant. I have to match the product. And there I use the guidelines. Now for my activation energy, here it matches. I just come down one, and there we've got the catalyzed. So again, reactant, product have to match. That's true in nature. And then the activation energy, catalyzed, just needs to be a little bit lower. It takes less energy to reach that minimum point, minimum energy for reactants to break, products to form. Let's go ahead and check this just because it's fun. I like it for the satisfaction that you can see that correct. All right, wonderful job. Please like and subscribe if you haven't already, and I'll see you next time. Bye.